So what I'm going to look at, this is just a supplement to the review. It's on logarithms and exponents. And I want to just talk about the relationships between logarithms and exponents. So it works like this. If we have a base to a power, we're going to get some kind of number, like 3 squared. 3 to the second power is 9. This is the same as saying that the logarithm of the same base of that number is going to give you that power back. Another way of thinking about this, b to the p is equal to n. So you go b to the p is equal to n, just kind of go counterclockwise around your logarithms. So let me do some examples. So 1/2 squared, 1/2 times a half is 1/4. So that's going to mean that we have a logarithm of base 1/2 of 1/4, and that's equal to 2. B to the P gives you 1/4. Same thing if we have 3 cubed, well, that's equal to 27. Or log base 3 of 27 will give us 3. Or something like this. 7 squared is 49. Or log base 7 of 49 gives us that power of 2. Now, you might be noticing something here. If we take a look at the power goes into the exponent, and then a number comes out. But then if we take that number and we put it into the logarithm, the power comes out. So the input, the output, and then the output, the input. It's almost like these functions are inverses of each other, and they actually are. So these are inverses of each other. Now, how is that the case? Well, let me give you kind of a brief proof. Now, there's an idea when we're working with inverses that if these are inverses, then the following is going to be true. And keep in mind, the bases for this to work, the bases have to be the same. If the bases aren't the same, this isn't going to work. But if functions are inverses, then we're going to see this property. If we put g inside of f, simplify things down, we're just going to get x. And we put f inside of g, simplify down, you'll also get x. So what we're going to try to do is letting f of x be this and g of x be the logarithm, we actually get this result. So let's start with f of x. So f of x, and let me write it slightly differently. So again, f of x is b to the x, or b to the x is f of x. Now, since this is the case, we can construct a logarithm. Base, power, number. So the logarithm of that base applied to the number gives us the power. Okay, that's just turning an exponent into a logarithm. B to the x equals f of x. Now here's the thing though. The logarithm base b of f of x, this is the same as replacing this x here in g of x with f of x. So if we put f of x here and here, we're getting this. So we really have g of f of x is equal to x. Because we replace x with f of x and replace this x with f of x, well, log base b of f of x, that's what we've got here. So you have g of f of x, and it's still equal to x. So far, so done. Now let's switch it around. So g of x is log base b of x. In fact, let me write this, switch the order here. There we go. So again, g of x is the log, or the log is g of x. Now we do our little counterclockwise trick. B to the g of x is equal to x. So we convert this into the exponent form. All right. But keep in mind, if we took f of x here, replace the x with g of x, that would put g of x up here like we have. So this is just f of g of x. And that's also equal to x. So this is just another way of verifying that these are inverses of each other. All right. So that being the case, since they undo each other, we're going to get a couple properties here. So b to the log base b of x is equal to x. So this would be f composition g. This is when we stick g of x inside of f. They're going to cancel and just give us x. And again, the bases have to match. If they don't match, this doesn't work. So we have f, and this is g of x, so f of g of x. So now let's take g of f of x. Well, f of x is b to the x. So we're going to get this. Again, the bases have to match. So what does this mean practically? Well, if we have log base 7 and then an exponent base 7, the log and the exponent will cancel. And we'll just get the power 4. Or if we have 7 with the power of a logarithm that has the same base, the base of the exponent and the log will cancel, and we just get 4. So I just want to go over some properties of exponents, and then what we'll do after that, we'll take a look at, we'll do some examples and look at some logarithm properties. So b to the x times b to the y. As long as the bases match, we add the powers. Now, if we have this, though, so we'll call this A, we'll call this one B. Well, now we're going to multiply. If we have this, we distribute the power as a power or as an exponent. But if we have something a little more complicated, we're going to get something like this. So I'm going to do some examples and just kind of illustrate how each of these properties work for exponents. And then again, we'll take a look at logarithms after these. So x cubed times x to the fifth. We're going to add them. We'll get x to the eighth. But if we have x to the third to the fifth, we're going to multiply them. We'll get x to the 15th. With this one, we just distribute the exponent as an exponent. And that's going to give us our answer. And then for this one, we'll distribute it as an exponent to the exponents. So we're going to multiply exponents and exponents. Excuse me. And that's going to be our set of answers. So let me do a more lengthy example. And this is something that's going to come up, or something like it could come up when you're simplifying algebraic expressions. Let's say we have this. There it is, z to the 7th. Well, we're going to distribute this. Now, since these don't have exponents, they'll just get a 2. Now, actually, what's going on, this is x to the 1, this is y to the 1, and you're getting 2 times 1 is 2, 2 times 1 is 2, 2 times 4 is 8. So 2 times 1 is 2, 2 times 1 is 2, 2 times 4 is 8. Now, as a shortcut, we just say 2 gets distributed to the variables that don't have an exponent, but really they do. It's the number 1. We're just multiplying the 1 and the 2. But the shortcut approach to saying you're distributing, that works. We just want to remember, though, that for this one, we show the multiplication. And then we have x squared, y cubed, z to the 7th. There we have x squared, y squared, z to the 8th times x squared, y cubed, z to the 7th. Now, since these have the same base, I'm going to add the powers, or the exponents. Same with these. Same with these. So what that gives us, x to the 4th, y to the 5th, z to the 15th. And that's going to be your answer. All right. So a few more properties with exponents. So if the bases match, we're going to subtract. Now, we can't do the subtraction if the bases are different. Now, if we have something like this, again, we have different bases. We're going to get this. Now, technically, what it's doing is x times the 1 to get 1 times x is x times the exponent 1 times x is x. It's just sort of a shortcut. We sort of distribute the x and just say it gets there. But for the next one, though, we want to be a little more precise. For this, that z gets multiplied to the other exponents. So for today, this is going to be the last of the exponent properties. And again, let me do an example with you on these, a few examples. So let's say we have this. So you have x to the 10 over x to the 7. Well, it's going to be x to the 10 minus 7 or x cubed. Again, because they have the same base, we subtract the exponent. For b, we have different exponents to the 10. And we can distribute the 10. Again, 10 times the 1 exponent is 10. 10 times the 1 exponent is 10. And there we go. Or, let's say we have this. Again, we're going to distribute the 3 as an exponent to the other exponents, and the exponents will be multiplied. And that's going to be our final answer. All right. 3 different answers for 3 different problems. So let me do one more. Then we'll take a look at some logarithm properties. So what I'm going to do first, I'm going to distribute this to each of these exponents. For up here, I'm going to use that property when we're multiplying exponents, where I can distribute this to each of those. And then I can also use the division property to distribute down to here. All right. So basically what happens when we have multiplication and division, this gets distributed everywhere. Where we can't do that is if we have addition and subtraction. At that point, we can't distribute it. But if it's just multiplication and division on the inside of the parentheses, we can distribute this to each of the exponents. Now for this here, I'm going to do KFC. So when we're dividing fractions, or in this case, rational expressions, I'm going to do this. I'm going to use the dot for multiplication. We're going to keep the first rational expression. We flip the second. We change division to multiplication, KFC. So we multiply everything together. And with multiplication, order doesn't matter. So I'm going to put my x squared over here, put my y here, and my z to the 8 over here. I mean, it's z times the x times the y, but multiplication, you can switch the order. So now we're going to use our rule. We're dividing exponents of the same base. Don't forget, when there's no exponent, again, there actually is one. It's just the number 1. For some reason, we write our ones as invisible. And then we have z 10 minus 8. All right. So that's the look at exponents as far as their properties go. Next, I want to look at logarithms. So properties of logarithms. So the log of a product is the sum of the logs. The log of a quotient is the difference of the logs. When we take the log of something that has an exponent, that exponent hops down. The log of 1 is equal to 0. And the log of 1 over something, well, it's just going to be negative log of that denominator. So there's one more key property with logs, and this is a real helpful one, especially if you're working with a calculator. So let's say we have this. So I'm going to do an example with this one. And why is this helpful with a calculator? Well, as you might recall from the examples that we were doing, we had a log base 7, a log base 1/2. Look on your calculator, you actually only have 2 log buttons. The first one is just log. And this is log base 10. So the log button on your calculator is typically log base 10. Now this isn't always the case. The other one is the LM, or this is called the natural logarithm. And this is log base E. Now sometimes in some computer programs, plain log will also mean log base E. So that's just something to keep in mind. The point is this. On your calculator, you can only calculate base 10 logs and base E logs. What if you need to do, say, like a base 3 or base 5 log? Well, let's say we've got this. Log base 3 of 7. Well, we can compute this as the log base E, or natural log, of 7 divided by the log base E, or natural log, of 3. Or it's going to be equal to the same number. Log base 10, or log typically on your calculator, of 7 over log base 10 of 3. Now, even though we're using two different logs, log base E, and I'll go into what E is actually, it's a number kind of like pi, or log base 10, regardless of which logarithm we use, we're going to get the same answer. And for us, it's going to be approximately 1.771244. So that property lets us use our limited logs on our calculator to come up with logarithms for really any base we want. Now E, I should mention what E is. So natural log is log base E for E it's about, let's see, 2.71828. It comes up in finance a little bit, or in calculations involving money. And if we have time, I'll go over that, how you can use it to come up with one of the compounding formulas when you compound continuously. You can compound or charge interest on a loan throughout the year if you want. You don't just have to wait to the end of the year. So you can compound, say, monthly, you can compound daily, or you can compound all the time. And when you do that, use a special formula that uses this number E. And if we have time, I'll go over that. I'll show you how you get that. You have to use an idea called a limit, which you're going to be studying in the next chapter. So there we go. Now, let's do a couple examples. For logarithms, let's say we have this. We're going to expand log base 2 of 100 x cubed cube root 5 minus x over 3 x plus 7 squared. So what we're going to do first, we're going to treat this as one whole piece, treat the denominator as one whole piece. We're going to use our subtraction. So we have log base 2, 100 x cubed, cube root 5 minus x, minus log base 2 of 3 x plus 7 squared. So now, since the log of a quotient is the difference of the logs, we're going to break these up. We have products. So the log of a product is the sum of the logs. So log base 2 of 100 plus log base 2 of x cubed plus log base 2, squeeze this in there, the cube root, 5 minus x. They're going to subtract, and this means we're going to get a sum. We're going to distribute at some point. Log base 2 of 3 plus log base 2 of x plus 7 squared. So in this next step, I'm going to do a little work here on these exponents. This is really 10 squared. When you have a cube root, that's really an exponent of 1/3. So I'm going to distribute this through here, this minus also. I'm going to take care of these exponents, get them out here. So that's 10 squared. Log base 2 of x cubed plus log base 2. And this is 5 minus x. Since we're taking the cube root of the whole thing, well, then the whole thing has an exponent of 1/3. Minus log base 2 of 3 minus, I'm distributing my minus sign, log base 2 x plus 7 squared. Now I'm going to do something about these exponents. Each exponent is going to hop down in front of the log, like so. Because we're taking the logarithm of something to an exponent. Since we have that kind of thing, the exponent jumps down. Now, if this 2, if I had like a 3 here on the x, I still have the 2, but let's say I had a 3. The 2 would hop down, the 3 wouldn't. It's going to stay on the inside. So it's only the entire piece that we're taking a logarithm of. We're taking the logarithm of the entire piece, and that piece has an exponent. That's the exponent that hops down. So doing that, let's see here. So we have 2 log base 2 of 10 plus 3 log base 2 of x plus 1/3 log base 2 of 5 minus x minus log base 2 of 3 minus 2 log base 2 of x plus 7. And that's going to be our answer. So let's do something like this. Let's do another one of these. Let's say we're going to do this. Well, let's say we're going to simplify this. Well, what we can do, take a look at this minus in here. Let's factor out that minus. If we factor out that minus, we can combine these. The sum of logarithms, and again, natural log, ln is log base e. The sum of logarithms will be a logarithm of a product. Now the difference of logarithms will be the quotient, the logarithm of a quotient. I'm going to do one thing first, though. I've got this 5 in front here. I'm going to make this a power, make it an exponent. So we'll put it back up like so. Now we can use the property. Difference of logarithms will be the logarithm of a quotient. All right. Now we can drop these brackets. We'll get 1/3 times the natural log of x plus 6 to the 5th, x times x squared minus 5. Now, this is something sitting next to a logarithm. So this is ultimately a power of the entire thing in the logarithm. So this means and an exponent of 1/3 is a cube root. So what we have is the natural log of the cube root of x plus 6 to the 5th over x squared minus 5. And so that's going to be our answer. Oh, 25. I'm sorry, this was 25. And the 25 didn't disappear. It's still 25. Sorry about that. Just keep an eye on your notes. It's always x squared minus 25. It should never be x squared minus 5. This did not change. All right. Well, I think that's about it for today. I just want to mention a couple properties with the natural log. And again, it's just like a regular log. It just has a base e. But you'll see it has kind of its does it sort of its own thing. So f of x is e to the x. G of x is the natural log of x. So again, the exponent and the log, they're inverses. So f of g of x is going to be equal to e to the natural log of x. And again, the base is e, the base is e, the exponent logarithm cancel out, and we're given x. Likewise, g of f of x, the natural log of e to the x, log base e, exponent base e, they cancel out, and we get x. So let me do an example of this. So all this is, again, these are both inverse functions of each other. So let's say you have this. Now we can do some rearranging here. This times this, rewrite it like that. And then we have something multiplied to our logarithm. It hops up here and becomes an exponent. And now we have an exponent base e with a logarithm base e. These are going to cancel. What we're left with is a to the x. So you see, that's going to be it for today. I'm going to do some more supplements. I do want to talk about the relationships between the graphs because they're inverses. They are going to have the property that they are reflections of each other across the line y equals x. And if you have the x and y values for the exponent to come up with the logarithm, just switch the x and the y's and there you go. You'll have points for the logarithm. We'll go over that on another time. Other than that, have a wonderful day.